All right, everybody. In this video, we are going to look at the first two sections of Chapter 1 that we cover, which are sections 1.5 and 1.6, which is all about what the limit of a function is and how that pertains to calculus. So let's first begin on talking about what is a limit. So let me read the definition for you, and I'll kind of break it down. Suppose f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a, except possibly a itself. And that last part's important. We'll get into that in a minute. Then we write the following. The limit as x approaches a of f of x equals L, or also can be said as the limit of f of x as x approaches a equals L. If we can make the values of f of x arbitrarily close to L, which means as close to L as we like, by restricting x to be sufficiently close to a on either side of a, but not necessarily equal to a. This part right here is super important. You do not have to equal a for limits to work as long as you are very, very close. Now, it's a lot easier if it does equal a, but we'll see both scenarios today. So, kind of show you graphically what a limit is. Here is a picture of a parabola, x squared minus x plus 2. And one of the questions is, what happens as x gets closer and closer to 2? So what you'll notice, and the pink arrows kind of give it away, but I'll add my blue flavor to it, is that as you get closer and closer to x equals 2 on the graph, from the left and the right, so from both sides, you see that we are approaching this spot right here. Now that spot, whether it exists or not, is called our limit. So if you go over and look at what the y value is, that gives us a value of 4. So on this problem right here, you could essentially say that the limit as x approaches 2 of f of x equals 4. Now, in this case, it does actually equal exactly 4, and that's great, but we'll see where that's not always true going forward. But you have to look both sides to see what y value you're getting closer and closer to. Now, to kind of show you again, I mentioned a second ago that it doesn't actually matter the value there as long as you're getting closer. If you look at these three graphs up here, and you note that if you take the limit as x approaches 3 on all of them, so if you look 3, 3, and 3, on all three of these graphs, as you approach closer and closer to x equals 3, you're getting closer and closer to the exact same spot. It doesn't matter whether it exists like it does in the first one, whether it doesn't exist like it does in the second one, or if your value is somewhere else other than where you're going. That does not matter. What you're asking yourself, what y value are you getting closer and closer to as x gets closer to, in this case, 3, and you can see it's always going to be 4. Now, if we can draw the graph, that's great, but as we're going to see throughout today, that not always a graph's not always needed. For example, what if you're asked to find the limit as x approaches 1 of x minus 1 over x squared minus 1? Now, your obvious thought may be, well, can we just plug it in? Will that work? Well, if you try to plug it in, you're going to get a problem of 0 over 0, and we'll get to what that means in a minute. But if you look at these two charts that I've provided to you, and I would provide these to you as well, is that if I start bigger than 1, let's say 1.5, as I get closer and closer to the number 1, and don't actually get there because you can't plug 1 in. As you get closer, you're getting really, really close to 0.499975. And going the other direction, if I start less than 1, in this case 0.5, and I get closer and closer to 1 from that direction, you get 0.500025. Now, you could actually get closer, but you need a calculator in order to do that. But can you tell what value you're getting closer to? Well, if you said 0.5, you are correct. That's also 1/2. So in this case, that would be your limit value. It didn't equal 1/2 exactly, but as you got closer to x equals 1 from both sides, you were able to see that you were getting closer and closer to 1/2. All right, so what about this one? Charts sometimes are done a little bit differently. As you can see that if you do something like the limit as x approaches 0 of sine x over x. Same problem. You can't plug 0 into this because that would give you sine of 0 over 0, and sine of 0 is 0, so you got the same problem. But as you can see from this graph or from the chart, it doesn't really matter. As you're getting closer to this x equals 0 from both directions, you see that from the left and the right, you are approaching that open dot right there. Now, it doesn't matter that it's open. Your question is, what y value is that equal to? Well, as you can see, that has a y value of 1. You can also see that from over here on this chart that I decided to combine two charts into one. So if you start on both sides of 0, so let's say plus and minus 1, as I got closer and closer to 0, you see that my decimal was getting so close to 1 that if I were to get closer and closer to 0 for x, you could almost see that it would almost pretty much be 1, that's why the limit value there is. Now, the problem can be is that we talked about that you got to look both directions. What if you only need one of them? So to kind of formalize my definition here, we say that the limit as x approaches a of f of x equals L if and only if you can look at both limits separately and get the same result. Now, there's two different notations here you're going to look at. If you see a limit as x approaches a number a with a minus as your exponent, this is known as the left-hand limit. If you see a plus sign as your exponent, this is known as the right-hand limit. And we're going to look at both right now. So based on this graph you see on your screen, can you focus on x is 2 and x is 5 as far as all three types of limits go? We're going to do the first one in blue, and that's the 2's. Let's focus on x equals 2. If you approach 2 from the left, so that's only from this direction, you see that you're getting closer and closer to that open dot. Remember, open dots are fine. If you look to the left, that's a y value of 3. Unfortunately, though, if you come from the right-hand side of 2, so start over here, and you approach 2 from the right, you're going towards a completely different open dot. Now, that's fine for right now. As you can see, that has a y value of 1. But based on our definition you see above, if both the left and right-hand limit don't equal each other, you don't have an overall limit. Now, that's fine. Since 3 does not equal 1, that means that your overall, that I'm going to call limit, does not exist. So you're going to see this abbreviation D and E a bunch over the rest of today. When I say D and E, that means the limit does not exist. But as you can see, if you work ahead a little faster than I do, let's focus on 5. So do everything around 5. You'll notice that if you approach 5 from the left, or if you approach 5 from the right, they are both approaching that same open dot that has y values of 2. Since both the left and right-hand limit are both 2, that's good. That means you do have an overall limit, which we can call 2 as well. Remember, this dot right here has nothing to do with the limit. That's just a function value. We'll get into what that means, I think, in the next video. All right, what if you need to get a limit that's not a real number? For example, infinity is very popular. So kind of reading through this definition really quick, let f be a function defined on both sides of a except possibly a itself. That's similar. We can say that the limit of f of x as x approaches a will equal infinity, or it could be negative infinity as well, means that the values of f of x can be made arbitrarily large the closer you get to your a value. Now, for example, an example of this would be the limit as x approaches 0 of 1 over x squared. As you can see from the graph, if we're focusing on x equals 0, as you approach 0 from the left and as you approach 0 from the right, you see both the left and right-hand side shoot up to a number that you can't see. And you can kind of see the closer we're getting to 0, the faster that it is increasing. You can also see from the chart right here, if I were to start, let's say, at 1 and negative 1, the closer and closer I get to 0, so let's say plus or minus 0.001, notice that each of these numbers is getting larger a lot faster. That's fine. If this happens, this means that your limit is equal to infinity. Similarly, If it had gone in the other direction, let's say that all the values shot straight down, then you could also say that a limit does become negative infinity, and we'll probably see one of those here in just a few seconds. Speak of the devil, here actually it is. So what does it mean when you get infinity as an answer for a limit? Well, as a word you've probably seen before, this means that you have a vertical asymptote. So what does the definition actually say? It says that the vertical line x equals a is called a vertical asymptote of the curve y equals f of x if one of the following 6 statements is true. You don't need all 6 of these, you just need one of the 6. Whether you're doing the overall limit, the left-hand limit, or the right-hand limit, if any of those limits become infinity or negative infinity, it doesn't matter which one, you can then say that you have a vertical asymptote at that a value. Now, I showed you the overall limit on the last screen. Look up here at the 4 graphs at the top. Here's an example of where, what if you just need the left and right? If you look at the left-hand limit here, or the right-hand limit on the second one, you see both of those are shooting up towards infinity, so they have vertical asymptotes. It also works if you shoot down, whether from the left or the right. If your limit shoots down towards negative infinity, then you also have a vertical asymptote. So that's going to play a big factor. So you are allowed to get infinity or negative infinity. It just means you have an asymptote there. So let's look at some examples. Can you find the limit as x approaches 5 only from the right of x plus 1 over x minus 5? Now you can't do 5 overall here because if you plug 5 into this, you're going to end up getting a 0 on the bottom, and that's not good. But think about what does it mean for 5 from the right to be? Well, if 5 from the right, now I can't write this whole number out, but remember, that's going to be a number that's very, very close to 5, but on the right-hand side. So maybe something like 5.00001. Now, technically, you would need infinitely many zeros here and eventually a 1 on the end. So what does that actually mean? If you were to plug a number really close to 5 into this function, well, that number plus 1 is going to end up being 6.0000 ... Eventually, you get a 1 on the end. What's more important, though, is that on the bottom, if you were to plug this in, you would get a 0.000 ... a whole bunch of zeros divided by 1. The question is, what happens when you divide a positive number by an infinitely small positive number? Well, you end up exploding into infinity. It's kind of like if you were to divide by a really, really large number, you pretty much get 0, but if you divide by a really, 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 really small number, you do get infinity. This also plays a key when you do stuff like trig. So what about something like the limit as x approaches 2 pi from the left of x cosecant x? Now what's actually going to help you here is if you were to rewrite this as the limit as x approaches 2 pi from the left. Remember, cosecant is just the reciprocal of sine, as we saw in the last video. So if I leave the x on top, I can flip cosecant over and make it a sine function on the bottom. Now, if I were to plug 2 pi from the left on here, remember, that's kind of the same thing. So from the left, that would be 1.999 ... pi. Well, if I plug that in, that would be 1.99 ... pi over. Now, what happens when you plug that into a sine function? Something you will have to recall is that in trig, when you learned how to draw sine functions, as you approach 2 pi from the left, you see these are negative numbers. So you would actually end up getting a negative 0.000 ... In the first example, if you divide this, you got a positive infinity. But when you take a 1.99999 pi, but divide it by an infinitely small negative number, this actually turns into and explodes into negative infinity. So you got to make sure you note that's what happens when you divide by really, really small numbers. Make sure you note the positives and negatives as well. But where you can save yourself a little bit of time is, what about example number 6, where it just says find the vertical asymptotes of the function? Well, you can do the limit here if you would like, or in algebra, you probably remember that if you were to find vertical asymptotes, your job was to simplify the function. If you look on the bottom, if you were to try to simplify this, you could factor an x off the bottom, and that would leave you a 3 minus 2x. Well, nothing cancels here, and that's fine. But what makes a vertical asymptote is what makes the bottom 0. We kind of saw that up here on these problems earlier. So if you were to just take the x, set it equal to 0, the 3 minus 2x, set it equal to 0, well, the first one's done for you. There's one vertical asymptote. The second one, if you subtract 3 from both sides, negative 2x equals negative 3, and then dividing by negative 2 gives you x equals 3/2. That's a faster way if you're just doing algebra to find vertical asymptotes. You can kind of see up here x equals 5 would have been easy. The trig one's a little bit harder. But in this case, if you want to find a vertical asymptote algebraically, just set the bottom equal to 0 after you have simplified. All right, so let's do one right here. The last one didn't simplify. Let's see what happens on this one. You've got y equals x squared minus 1 over x squared plus 3x plus 2. Well, if I were to factor the top and bottom of this fraction, the x squared minus 1 does factor into a difference of squares, so that is x plus 1 times x minus 1, and the bottom can be factored into x plus 2 times x plus 1. What's different about this one, as you can see, is that this x plus 1 divided by this x plus 1 does cancel, and you're left with an x minus 1 over an x plus 2. To find the vertical asymptote of this, just take the new denominator, which is x plus 2, and set that equal to 0. If you subtract 2 from both sides, you get x equals negative 2. And that is the only vertical asymptote of this function. Now you may be curious, what about the plus 1? Where does that go? We're going to see that in the next video. What happens when you cancel off something, and what does that become? That's something we're going to talk about in the next video. All right. There's not really much to that first section, so that was kind of the shorter part. 1.6 is a little bit longer because we're not going to do as much graphing or infinities here. Instead, we're going to talk about limit laws, also known as algebraic limits. All right, I'm not going to spend a lot of time on the video on this one, but if you want to pause and write this down, you can. Essentially, these are just some algebraic rules that you are allowed to use in limits. I'm going to run through these really quickly, and then we'll kind of use them along the way. Essentially, it says is that if you've got two functions being added or subtracted, you can break those up and do the limits separately. If you have a constant in the front, you don't have to worry about the constant. Just do the limit of the function, and then you can apply the constant at the end. If the two functions are being multiplied or divided, kind of like addition and subtraction, you can break those up separately and do them as separate limits. Once again, if you want to pause the video at this point and write these down, go for it. But like I said, I'm not going to spend a lot of time on these because we kind of do them along the way. All right, here's the more important thing for me. This is called the direct substitution property. If you are finding the limit of a function, as long as it's whether it's a polynomial or rational function, as long as a is in the domain of f, then you can find the limit as x approaches a of f of x by just plugging a into the function. That's going to be fantastic. But we have to make sure that it is continuous, and we're going to know when that doesn't happen. So how do you know if it's not continuous? There's a big giveaway. If you plug a into your function and you get 0 over 0, it's not continuous. That's not good, but there's an easy way to fix that. We're going to talk about how do you simplify your function in order to find the limit. So there's going to be a lot of algebra over the next 30 minutes or so make sure you're prepared to be able to simplify rational functions. All right, so first example. If you have the limit as x approaches 5 of x squared minus 6x plus 5 over x minus 5. First thing we're going to do a lot in this section is plug 5 in. If you plug 5 in, you'll get 5 squared minus 6 times 5 plus 5 all over 5 minus 5. That's going to end up giving us 25 minus 30 plus 5 over 0. And if you simplify the top, you will also get 0. Ding, 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 ding. When you get 0 over 0, your function should have simplified from the beginning. So what I'm going to look at here is that if I take the limit as x approaches 5, how could we simplify this? Well, the first instinct is to try to factor it. While the bottom does not factor, x minus 5 is the best you're going to be able to get, x squared minus 6x plus 5 can be factored into x minus 5 times x minus 1. And there you go. You see that x minus 5 over x minus 5 does cancel, and you're left with the limit as x approaches 5 of just the x minus 1. Once you have simplified, replug your 5 back in. This would be 5 minus 1, which is 4, and you're done. Now what happens if you plug in and get 0 over 0 again? Well, then it means you didn't simplify right, or you got to simplify a little bit further. So make sure you are careful when you're simplifying that you simplify as far as possible before plugging your value back in. Now just to show you that you will not always get 0 over 0, here's my example. So in this example, it looks very similar, but if you notice, when you plug 5 into this one, you're going to get 5 squared minus 5 times 5 plus 6 over 5 minus 5. In this case, you get 25 minus 25 plus 6 over 0. Now this is not 0 over 0, and that's fine. It's actually 6 over 0. That is an answer you will get from time to time with a 0 on the bottom, but not a 0 on top. You don't need to do any other work. Your final answer is D and E, because you cannot do 6 divided by 0. That value does not exist, but there's no need to simplify even if it does. So that problem right there, you'll be happy when that happens. You're all done with this. All right, so for the rest of these, I'm going to show you maybe some factoring techniques or simplifying techniques that maybe you haven't done in a while. That way everybody can kind of see what you're expected to be able to do. For example, what about the limit as x approaches negative 2 of x plus 2 over x cubed plus 8? Now you can very quickly verify that if you plug negative 2 into this, let's see, negative 2 cubed is negative 8. You're going to end up getting that 0 over 0 case. That means something does simplify. Usually it's going to be factoring, so let's see. This will be the limit as x approaches negative 2. Now while the x plus 2 does not cancel, x cubed plus 8 is a sum of cubes formula that you probably maybe haven't seen in a while unless you've had algebra more recently than others. So back in algebra, you learned a formula, and I'm going to use a's and b's, that a cubed plus b cubed, that's a sum of cubes, can be factored into a plus b times a squared minus ab plus b squared. In this case, to find a and b, a is going to be the cube root of the first number, so the cube root of x cubed is x, and b is going to equal the cube root of the constant, which is 8, which we should know is 2. You need to plug that a and b value into this factored form. So doing that should give you x plus 2 times x squared minus 2x plus 4. The whole point of this is you now can see that x plus 2 divided by x plus 2 does cancel and leaves you with the limit as x approaches negative 2. Since everything canceled off the top, that leaves us with a 1, and we have an x squared minus 2x plus 4 on the bottom. Replug your negative 2 in. This should be 1 over negative 2 times negative 2 is 4. Negative 2 times negative 2 is once again 4, and then you have another plus 4. You get a final limit value of 1 over 12. So as you can see, once again, factor what you have, simplify, and then replug your value back in to get the limit value. Now, will everything be a fraction? No. Sometimes in this class, it's very, very straightforward. Something like, what is the limit as x approaches 0 of cosine of x? Well, there's no fraction, so there's no way you're going to get 0 over 0. Just plug your number in and evaluate. If I plug 0 in, you get the cosine of 0, which from our trigger view, we know is 1. That's it. Take advantage. That's going to happen a lot more than you think it does. Not everything is super complicated, but don't mess up on the easy ones when they're given to you. All right, so for the next few problems, let's look at some that maybe aren't as straightforward, because I want you not only to be able to do the easy ones, but I want you to be able to use your thinking caps to do the more difficult ones. For example, what is the limit as h approaches 0 of 3 plus h all squared minus 9 all divided by h? Now, if you would like to, I'm going to let you do this yourself, but just to save some time, if you try to plug h's 0 in, you're going to get 0 over 0. That means something simplifies. Now, there's a few different ways I can think of. This does factor, but most of y'all probably won't recognize the factoring right away. So my philosophy is just simplify it. Just multiply stuff out. What if we were to rewrite this as the limit as h goes to 0 of 3 plus h times 3 plus h minus 9 all over h? Foil those first two terms together. This is the limit as h goes to 0 of 9 plus 3h plus 3h plus h squared minus 9 all over h. Well, one good thing comes of this. This 9 minus this 9 does go away, and you're left with the limit as h goes to 0 of 6h plus h squared all over h. And we saw this during the algebra review when we were doing the difference quotient problems. It looks very similar. You can factor in h off the top and leaves you with a 6 plus h left over. But by doing that, we can now easily see that h divided by h cancels. And if you're left with the limit as h goes to 0 of 6 plus h. And if you now replug your h equals 0 in, you don't get 0 over 0 anymore. You get 6. So that is going to be your limit value in this case. Very good. All right, let's change it up a little bit. Let's not square that term. Let's instead do a square root problem. What about the limit as h goes to 0 of the square root of 9 plus h minus a 3 still being divided by h? Now, as some of y'all can tell, if you try to plug 0 into this, the square root of 9 is 3. 3 minus 3 is 0, and you also get a 0 on the bottom. So, can't do that. This one's a little trickier because it doesn't factor and it doesn't expand. You're going to have to be very clever about what you do here. So let me show you what I would do. I'm going to do the limit as h goes to 0. Let me just rewrite the problem for you. Square root of 9 plus h minus 3 over h. My suggestion to you is that if you have a square root that you're trying to simplify because you're getting a 0 over 0, let's do a very clever way of multiplying by the conjugate. This square root is causing the problems. So what I would do is I would take the square root of 9 plus h, and instead of subtracting 3, let's multiply it by a plus 3. And you'll see why in a second. But in order to not change the problem, I need to do the exact same thing to the denominator. So when I do that, this now becomes the limit as h goes to 0. Now the bottom, remember the bottom's not the problem. I'm going to leave this as h times the square root of 9 plus h plus 3. It's the top. Now the good thing is that if you try to multiply all of this out, since this is a factored form of a difference of squares now, you can now simplify it when you multiply it together. The only two parts you have to worry about is first, multiply the first terms. The square root term times the square root term will cancel the square roots and just leave you with a 9 plus h. The outer and inner will always cancel in this format, so don't worry about those. But then you can multiply the last terms, which is the negative 3 and the positive 3, which leaves you with a minus 9. As you can now see, two things are going to happen. Number one, 9 minus 9 cancels. Then you have the h divided by an h times a bunch of other stuff. Well, this h over this h cancels, and all of that now simplifies you down into just a 1 on top. So now that you have a 1 on top, it's impossible to get 0 over 0 again, so you can now replug your h equals 0 in. The 1 on top, the 1 on top won't change. If you plug it the h equals 0 in the bottom, you get the square root of 9 plus 0 plus a 3, which is equal to 1 over the square root of 9 is 3. And as you can see, your final answer is going to be 1/6. Very good. So if you have a square root that does not factor and does not simplify nicely, try to use the idea of a conjugate to see if it simplifies like this one did. All right, number 7. What is the limit as x approaches 3 of 1 over x minus 1/3 over x minus 3? Same idea, just to kind of save a little bit of time. If you try to plug 3 into this, you'll get 1/3 minus 1/3, which is 0, over 3 minus 3, which is also 0. So nothing wins there. This time, though, doesn't factor. There's not a square root. Instead, you have these extra fractions. We saw this in the composition stuff that we did in the algebra review section. We don't like this x and we don't like this 3 being on the bottom. So what I would do is I would multiply the top and the bottom by what you're trying to get rid of. If you're trying to get rid of an x, multiply the top and bottom by x. If you're trying to get rid of a 3, multiply the top and bottom by 3. When we do that, you're left with the following. It is the limit as x approaches 3 of, you'll have a 3x times 1 over x minus a 3x times 1/3 over a 3x times x minus 3. All I'm doing is taking this 3x and I'm multiplying it by everything on the top and the bottom. Now, once again, kind of like the square root problem we just saw, I'm not worried about the bottom. The bottom will fix itself in a minute. Let's simplify the top. This is the limit as x approaches 3. On the first fraction, you'll see that your x's cancel, and on the second fraction, your 3's will cancel, which leaves you with 3 times 1 is 3, minus x times 1 is x, over 3x times x minus 3. Now, these 3's don't cancel. Please don't do that. Instead, you should notice that this 3 minus x and this x minus 3 are very similar to each other, except that they're backwards. You need to make sure that they're in the same order when subtraction is involved. So the easiest way to fix that is you can do the limit as x approaches 3. If you factor a -1 off the top, you can flip-flop your subtraction, because the 3 becomes a -3 and the negative x becomes a positive x when you factor a -1 out. By doing that and not touching the denominator, you can now see that x minus 3 over x minus 3 is canceled, and you are left with the limit as x approaches 3 of a -1 over 3x. And if you plug 3 into this, 3 times 3 is 9, and your final answer is -1/9. So that's how you will deal with when you have those complex fractions involved there. All right, so we saw one similar to this a minute ago, but I wanted to show you that sometimes the powers do get a little bit bigger. So what about something like the limit as h goes to 0 of x plus h cubed minus x cubed all over h? Similar to the squared problem we saw a few slides ago, the problem is that x plus h cubed. We need to expand this because that's going to be the fastest way, I believe, to do it. So right here below, I'm going to kind of go a little bit off key a little bit. I'm going to multiply x plus h by itself 3 different times. Now the first time you do this, so let's do the first two, x plus h times x plus h, that's going to be FOIL. So that would be x squared plus xh plus xh plus h squared times the other x plus h. Now you can simplify that first one a little bit. It does become x squared plus 2xh plus h squared times another x plus h. And while you can't FOIL again, that's fine. What I'm going to do is I'm going to first take the x and multiply it by all three of those terms. That would be x cubed plus 2x squared h plus xh squared. Then I'm going to take the h and multiply it by the same three things, which is plus x squared h plus 2xh squared plus an h cubed. And if you combine your terms here, you should get an x cubed plus 3x squared h plus 3xh squared plus an h cubed. Now that is not your answer. You must now take this and plug it into where you have the boxed in stuff at the top. This would be the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus an x cubed, that's the minus part there, all divided by h. All that happens here is that the very first x cubed and that minus x cubed you have do cancel. And you'll also see, and I'm going to skip one little step here, you will now be able to notice that there is an h in common with everything that's left over. So if I factor the h out of all three terms, you have a 3x squared plus a 3xh plus an h squared, all divided by h. And very nicely, this h you factored out and the h on the bottom now cancel. Now that your fraction is gone, you can plug your h equals 0 in, and the two terms that have h's involved are going to actually go away, and you're going to be left with an answer of 3x squared, technically plus 0, and that's going to be 3x squared. Now, you may be thinking, well, didn't you skip a step at the very beginning? Well, I did. Once again, if you plug h equals 0 in, you will get 0 over 0. I went ahead and skipped that step. A lot of these that we're testing in this section are 0 over 0, so you can get used to simplifying. Now, keep in mind this problem right here. We're going to see something very similar to this in Chapter 2, which I believe starts in the next video that I'm going to put out. So that's going to come back, and we're going to talk about what does it mean when you get something like that when you apply that particular limit, because that limit as h goes to 0 is very important at the very beginning of Chapter 2. All right, so the last thing I want to do with y'all today is talk about absolute values. So absolute values can kind of cause a problem depending on how they're done in the problem. So for example, what if you're asked to do the limit as x approaches 3 of 2x plus the absolute value of x minus 3. So here's how you'll know if you have a problem or not. If you can plug the limit into your absolute value and it gives you an answer of 0, that's good. That means there's no tricks and you can just go along your business and finish this problem. So let's check. Does 3 minus 3 equal 0? Well, of course. So all you have to do is do 2 times 3 plus the absolute value of 3 minus 3, which we already talked about. That whole thing's going to go to 0. And then 2 times 3 is 6. That is a best case scenario right there. If the absolute value term goes to 0, you don't have to do any extra work. The problem we're going to see on the next one is what happens when your absolute value does not go to 0. What must you do at that point? Well, here's your case. What is the limit as x approaches -6 of 2x plus 12 over an absolute value of x plus 6? Now you're looking at that and going, hang on. It goes to 0. But do you see the problem? Yes, you cannot have a 0 on the bottom in this case. So what you're going to notice is that if you have an absolute value function on the bottom, my suggestion to you will be break this up into 2 different limits. And here's what I mean. We're going to do the limit as x approaches -6 from the left. And what is the limit as x approaches -6 from the right? We saw this in section 1.5 about 30 minutes ago or so. Why do we need 2 different functions? Because what you probably don't remember, and that's fine, is that an absolute value function is actually a piecewise function that has one function defined as a positive and one function defined as a negative. Now the negative one is defined for less than 0 and the positive one is defined for greater than 0. Now how does that help us? When you do your left-hand limit, left hand usually means less than. So I have to now apply a negative when it comes to my absolute value. So you've got your 2x plus 12, which I'm good with, but instead of doing the absolute value of x plus 6, I must do the opposite of the inside. We're going to do the negative of the x plus 6 versus the right-hand side, which usually means positive, or in this case greater than 0. You don't have to change a thing other than dropping the absolute values off, which would just be x plus 6. Now on both of these, you're going to notice that you get that 0 over 0 case. That's fine. That means you should be able to factor something. On the left-hand limit, if I do the absolute value of negative, I'm sorry, I misspoke. If you do the limit as x approaches negative 6 from the left, you can factor a 2 off the top, which leaves you with 2 times x plus 6 over a negative of an x plus 6. You'll notice that the x plus 6's cancel, and remember that is an understood negative 1 you have right there, so there's actually nothing to plug in. 2 divided by negative 1 is negative 2. Similar, if you plug negative 6 into this, you're going to get 0 over 0. So when you factor this one in the exact same way, you get the limit as x approaches negative 6 from the right of, once again, 2 times x plus 6 over x plus 6. The x plus 6's cancel again, but you're not left with a negative 2. You're actually left with a positive 2. Now think back to about 30 minutes ago. You got a left-hand limit of negative 2 and a right-hand limit of positive 2. What does that mean that now your overall limit's going to be? Well, your answer is going to be does not exist. If you have to deal with both limits, now you could have done this, we could have actually done this technique on the last problem and we would have seen that we would have gotten the same answer on both. The problem with this one is that the 0 absolute value occurred on the bottom and not on the top of this fraction. All right, and last but not least, I want to do a thinking question with you. So this is going to wrap up our section 1.6. Can you tell me, is there a number a such that the following limit does exist? So you have the limit as x approaches negative 2 of 3x squared plus ax plus a plus 3 over x squared plus x minus 2. You'll notice that all of the a's are in the numerator, so we'll deal with that in a second. Since usually the first rule of thumb is to plug in your x value, what happens when you plug in negative 2 on the bottom? Well, you get negative 2 squared plus a negative 2 minus a 2. And if you do a little bit of math here, that's going to be 4 minus 2 minus 2, which gives you a 0 on the bottom. Now, if you get any number on top, most of that's going to be does not exist. Remember, the question's asking us, is there a value where the limit will exist? Well, the answer is, well, we can force that. Dot, 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 dot. We don't know what this is, dot, dot, dot. What do you need the top to be? You need the top to also be 0. Because if you can force it to be 0 over 0, then you know that it simplifies in some way to get a limit value. So I'm going to concentrate on the top here. I need 3x squared plus ax plus a plus 3. I need this to equal 0 at x equals negative 2 because that's the limit value here. So plug in x equals negative 2. That's 3 times negative 2 squared minus 2a plus 3 is 0. Negative 2 times negative 2 is 4. 4 times 3 is 12. Negative 2a plus a is minus a plus 3 equals 0. 12 plus 3 is 15 minus a is 0. And there you go. Add the a over. And 15 has to be the value of a. Now, at this point, if you want to practice, you could actually plug the 15 in and work this out, but that's not what that question is asking for us. It wants to know, is there a number a such that the limit exists? Yes. If you plug 15 in and apply the limit, you will get 0 over 0. Therefore, it will factor and simplify, and you can find the limit value. So the big talk today was all about limits. We did some graphical limits in the first section. In this section, we did algebraic limits with limit laws. In the next video, we're going to keep talking about limits a little bit and get into continuity. And then we're also going to define what the definition of a derivative is, which is the backbone to Calculus 1.